Hello, we're going to discuss 4.5 Optimization 2 today. This is a continuation of the topic in 4.4. We're going to discuss the applications of derivatives in economic optimization. Typically, guidelines for solving optimization problem include the following four steps. Step 1. Assign a label to each variable mentioned in the problem. If appropriate, draw and label a figure. Step 2. Find the expression for the quantity to be optimized. Step 3, use the conditions given the problem to write the quantity to be optimized as a function f of one variable. Note any restrictions to be placed on the domain of f from physical conditions of the problem. Step 4, optimize the function f over its domain. We're going to start from a maximization problem. A city's Metropolitan Transit Authority, or MTA, operates a subway line for commuters from a certain suburb to the downtown metropolitan area. Currently, an average of 6,000 passengers a day take the train, paying a fare of $3 per ride. The board of MTA contemplating raising the fare to $3.50 per ride in order to generate a larger revenue. Engage the services of a consulting firm. This firm study reveals that for each 50 cents increase in fare, the readership will be reduced by an average of 1,000 passengers a day. Therefore, the consulting firm recommends that the MTA stick to the current fare of $3 per ride, which already yields a maximum revenue, so that the consultants are correct. We're going to follow the 4 steps strictly and do the problem. Let X denote the number of passengers per day, P denote the fare per ride, and R be the MTA's revenue. The rate of change of x with respect to p is just negative 1,000 over 0.5, which is negative 2,000. We know for each raise of 50 cents in the fare, we have a reduction of 1,000 passengers. So the change of x from the current value x minus 6,000 equals the rate of negative 2,000 times the change of p from the current value p minus 3. Currently the fare is $3, and the passenger number is 6,000. So we obtain x minus 6,000 equals negative 2,000 times p minus 3, and we can rewrite it as p equals negative 0.0005x plus 6. The range function is then r equals x times p, which is x times negative 0.0005x plus 6, and we get negative 0.0005x squared plus 6x. Since the price of fare p greater than or equal to 0, we have negative 0.0005x plus 6 greater than or equal to 0, so we get the x less than or equal to 12,000. Also, x is the number of passengers per day, so it has to be non-negative. So x is in the interval from 0 to 12,000. So in step 4, we need to maximize the function. The revenue r equals negative 0.0005x squared plus 6x on the interval from 0 to 12,000. Take the derivative of the revenue function, we get the negative 0.001x plus 6. Set it equal to 0, we solve for x equal to 6,000. And plug in 6,000 in R, we get the negative 0.0005 times 6,000 squared plus 6 times 6,000, and we get 18,000 for the revenue. Compare this value with R of 0, which is negative 0.0005 times 0 squared plus 6 times 0, we get 0. And R of 12,000, which is negative 0.0005 times 12,000 squared plus 6 times 12,000, we also get 0. So we conclude that the current price of $3 is the optimal solution. You can take the second derivative of the revenue function R to get the negative 0.001. So that's negative. According to the second derivative test, the function R attains a maximum at the critical value of x equal to 6,000. Now let's do another problem of minimizing the cost. This is the inventory problem. Dixie Import-Export is the sole agent for the Excalibur 250cc motorcycle. Management estimates that the demand for these motorcycles is 10,000 per year, and that they will sell at a uniform rate through the year. The cost incurred in ordering each shipment of motorcycle is $10,000, and the cost per year of starting each motorcycle is $200. Dixie's management faced the following problem. Ordering too many motorcycles at one time takes up valuable storage space and increases their storage cost. On the other hand, placing orders too frequently increases the ordering costs. So how large should each order be, and how often should the orders be placed to minimize ordering and storage costs? We're going to follow the steps to solve the problem, but I'm not going to write down explicitly. So let's denote the X, the number of motorcycles in each order. So that's the lot size. If we assume that each shipment arrived just as the previous shipment has been sold, the average number of motorcycles in storage during the year is X over 2. We know we got a large number of motorcycles in storage sometimes, but at other times we might have a small number of motorcycles in storage. So we just take the average, and we get X over 2, where X is the number of motorcycles in each order. So that's the largest number of motorcycles in storage. Then Dixie's storage cost for the year is just 200 times X over 2, which is 100X. For each motorcycle, we need $200 for the storage cost for the whole year. And the number of orders required per year is 10,000 over X. The total number of motorcycles in the year is 10,000, and X is the number for each order. So the number of orders per year is just 10,000 over X. And the ordering cost per year is $10,000 times this number of orders, 10,000 over X, which is 100 million over X. We know for each shipment of a motorcycle, it takes $10,000. So the total yearly cost includes the shipping fee and the storage fee. So that's 100X plus 100 million over X. Take the derivative of this total cost, we get 100 minus 100 million over X squared. Set equal to 0. We solve the equation, we get the X equal to 1,000. And there's another non-physical solution of negative 1,000, but you cannot have a negative number of motorcycles in each order. So we just reject it. Take the second derivative of the total cost, we get 200 million over X cubed, since X has to be positive. So this C double prime is always positive. That means the total cost C is concave upward everywhere, and so we obtain a absolute minimum at X equal to 1,000. So the optimal number of orders per year is just 10,000 over 1,000 equals 10. 10,000 is the total number of motorcycles per year, and 1,000 is the number of motorcycles in each order. So the number of orders is just 10,000 over 1,000, which is 10. So this is the end of this section.